All right, recording is rolling. It's Tuesday, January 31st. So yesterday, you guys remember we were going through these puzzles. We knocked out chapter 16, Fundamentals of Light. There were a few new concepts there. Okay? But now we started chapter 17, Reflection, which we did last week, and we're about to go to chapter 18, Refraction, which we also did last week. So that should be a review type stuff. Hopefully, you guys can see stuff ahead of me with those as we go through this. Okay. And then I got some demos lined up for you guys, but my first honors class today. We're going to see exactly how far we get today with that. There's a fundraiser going on today. Go to Mr. Delicious Pizza after school. Then some of that will go to UNICEF. So there you go. All right. So I think the last one we did yesterday was jeweler's mirror. Okay. We've got a jeweler with a watch of a certain size placed in front of a concave mirror. Remember, like, why you would do that? Because if you have like an object within the focal distance of a concave mirror, like this one is, then it should blow it and make it bigger. We're going to say like how big should it be? Where should the image be? It should be a virtual image. So the location of the image was like the negative value. Say the virtual image is on the opposite side. Okay? And we actually, I think, solve this from two different points of view. You can solve it with this equation: 1 over focal distance is 1 over distance image plus 1 over distance object. You can also solve it with a ray diagram, and it should both give you about the same answer. Okay. All right, so okay. Are we good on 71 then? Good, okay, so next one, number 64. Comes a little bit out of order. It's all right. Describe the image produced by the object as real or virtual, inverted or upright, and smaller or larger than the object. Okay, so now we got another concave mirror, just like the last one we were looking at yesterday's concave mirror. Okay. The difference, though, I'm thinking is that the objects, which they've shown as an arrow, so it is like outside the focal length. Right? Yesterday, like the watch yesterday with jeweler's mirror, the watch was like about here. Okay? But now the object's like out here. Okay? Now, remember, I like to use stick figures. Paul Hewitt likes candles. A lot of textbooks just use arrows, but so your textbook uses arrows. Okay? So let's do that. What happens when the object is outside that focal distance? But notice it's also here. What do you guys think C stands for? Maybe the center of the circle that would fit flush to this parabolic mirror, right? Right, guys, remember the focal distance is like half the distance to the mirror, or to the center of the circle. You guys remember that? I told you guys that about a week back. Okay. So guys, gonna try to recreate that pretty close, and we'll solve this with a ray diagram. This is number 64. Okay. Had a mirrored surface. And let's do focal point. How about it's right about there, and the object is like right about here. I'll go back to stick figure. So here's focal point. Okay. So if you have a concave mirror and the object is just a little bit outside that focal distance. All right. So you guys remember for reflection, there's of course rays of light going all different directions, but we can just follow a couple of rays and figure out where the image is going to be. One is going to be say like parallel to the floor across top of the head. That's going to bounce the point straight to the focal point. It's going to be reflected that way. Okay? Another ray of light might go through the focal point, hit the mirrored surface, and then be reflected back parallel to the ground. Ooh, now this has a really weird outcome. It looks like it's going to be here. I have to kind of extend this far left side of the page here. Okay. Ooh, yeah, I don't think we've come across one that's exactly this category yet. Okay. But it looks like it's being projected upside down. Like, what if I had like a projection screen over here? Right, there's like a projection screen. It's like right there. Bam. Right. This thing would be so let's go down a checklist of things we're supposed to answer here. Right. First of all, is that a real or a virtual image? Real or virtual? Real. Yeah, and it's real because it's in front of the mirror. So it's real. Is it inverted or upright? What do you guys say? Yeah, inverted. Okay. And then if you compare the sizes, is it larger or smaller than the original object? Larger. Right. So here's object. Here's the image. Right, just like that. Okay. And let me check that with the equation. So 1 over f equals 1 over distance object plus 1 over distance image. Okay. So on my paper here, I'll make the numbers a little bit different, but it'll be proportionally about what it is. But I think I had this as like 8 centimeters, and this is like 12 centimeters. So let's try that. Let's do 1 over 8 centimeters equals 1 over 12 centimeters. Let's solve for distance image and pretend we don't know it's like over there. I mean, it should be, here, let's see if it's consistent with the picture, right? So I'll do 1 over 8 minus 1 over 12, and then take the reciprocal of that. So a few algebra steps later, I'm getting 1 over 8 minus 1 over 12 centimeters, right? So something like that. Okay. Subtract this over, then reciprocal. 1 over 8 minus 112. Okay. Distance image is, okay, according to the math, it should have been at 24 centimeters. The fact that it's positive means it's on the same side as the object, exactly like the ray diagram shows. And looks like it should be twice as far out as the object was if everything was proportionally exact. Okay. And okay, so that's kind of in the ballpark. Exactly what the ray diagram shows. Right, so it's right there. So the equation pretty well aligns with the diagram. Number 66. Find the image position and height of the object, because they're really similar thing. Now, do you guys see how this object is? It's almost twice as far away from the focal point. So I think it's going to be the same category as the one we just did. It'll probably have a really similar result. Okay. Actually, okay, so the ray diagram is probably not going to look a whole lot different. I'm going to just jump straight to the equation for this one, number 66. Just jump straight to the equation. 1 over focal length equals 1 over distance object plus 1 over distance image. So they gave us a focal length of 16 centimeters. And the object is almost twice as far out, but not quite. So where should the image be? Okay. Well, I'll subtract over 1 over 31 centimeters, then take, so I'm throwing an extra algebra step. Okay. 1 over 16 centimeters minus 1 over 31 centimeters. Okay. Which number is bigger? Let me make sure you guys are following this. Which number is bigger, 1/16 or 1/31? Yeah, 1/16 is a bigger number. So when I subtract this two, is that positive or negative? Positive. Okay. I mean, same thing we just did. Again, I think it's going to be like the same category of problem. Okay. Okay, so 1 over 16 minus 1 over 31. Okay. Then the other thing you have to do is take the reciprocal of that. So when you take the reciprocal, that's telling me 33.1 centimeters. Okay. Oh yeah, this is like almost exactly what we just did, because the image is showing up, but like kind of like behind the object. So it's actually the same thing, like have a projection screen like behind the object, but still in front of the mirror, right? It's really similar looking picture. Okay. Now the question really though was, okay, so 2 parts. One was what is the position? So there's the answer to what's the position, about 33 centimeters from the mirror surface. Okay. The follow-up question was, what's the height of the object? Now, I remember the last one that we just did, looked like the image was blown up a little bit. Okay. The fact that it's like further away, that the image is further away than the object is from the surface, it's going to be blown up a little bit. So I think this will also be true. And we have an equation that we can use to navigate this, and this is the magnification. You guys remember magnification? Is the ratio of the height. Like, what's the height of the image compared to the height of the object? Oh, well, that would be what magnification is. Right? So 3 times as big. Right? But you can alternatively get that by taking the ratio of the distances, distance image over distance object. And then, okay, they say make it negative, so like invert it. Negative. Okay. So that's part A. Part B is going to be magnification is equal to. Yeah, here, there's a little detail I just want to mention. If there was like 3 lines like that, right? Why is it 3 lines? See right now? Okay. So I'm just going to treat that as an equal sign. If you see 3 lines like that, it means it's defined as. So the definition of magnification is the ratio of the heights, which is also equivalent to therefore blah blah blah. Okay. All right, so I'm just gonna say equals. We're looking at distance image compared to distance object, so make it negative. So we're doing negative 33.1 centimeters compared to the object was here at 31 centimeters. Okay. Yeah, so it magnifies a little bit, but hardly anything. So what is that divided by that? So it's 1.067 times magnification. So it magnifies by about 7% maybe. Okay, just a little bit. Okay. And the fact that it's negative in this context means it's inverted, it's upside down. Okay. Can you do that? Figure out magnification by taking ratio of heights, or in this case, ratio of distances. All right, here's it. All right, and then the last one on the reflection looks like looking at the backside of a spoon, or maybe the physics term would be a convex mirror. Right, so we're back to convex. Ooh. So see if you guys can stay a step ahead of me with this one. 75. So convex mirror. Got a focal distance of say like 4 centimeters this way, and the object is twice as far out in the other direction. Bam, bam. It's right about there. Go with my stick figure again. About that. Okay, so see if you can stay a step ahead of me. I think the answer is that poster up there, or if you remember back to the ray diagrams that we did. So here's a ray parallel to the ground that way. It's gonna bounce, it's gonna reflect up and to the left. We're gonna line that with the focal point. Bam, just like that. Okay. I'm gonna backtrack, extrapolate, say, okay, well, it looks like that's where the ray came from. Okay. It doesn't really cross the mirror, but it looks like it came from there. Okay. Then we'll have another ray go from the top of the head straight towards the focal point, and that particular ray is going to bounce off the mirror back parallel to the ground. Therefore, it looks like it came from that direction. You guys see where the two lines converge right there? There is the location of the image. Image right there. Okay. Now, again, I'm doing all these two ways. You can do both ways or just one way. It's up to you. But here's the equation version: 1 over f equals 1 over do plus 1 over di. Let's see if that's consistent. So your book told you this distance was 4 centimeters. I'm going to make it negative, which would in this case indicate a convex mirror. So 1 over negative 4 centimeters equals 1 over object was 8 centimeters in the positive territory. 1 over di. Right. Now, if all this works, the image location should be negative on the same side as the focal point, and also not as far out as the focal point, right? Because it looks like it converge to the focal point, but it's always going to be like, if you look at the backside of a spoon, pretty much this is kind of the only category of outcome you can get. Okay. So let's try that. I'm going to subtract over 1 over 8. So 1 over negative 4 minus 1 over 8. Okay. So 1 over di is negative 0.375, 1 over centimeters. Then take the reciprocal. Right? Reciprocal distance image is mathematically negative 2.67 centimeters. Yep, that is definitely consistent with the picture we just did. Oh yeah.
How would I take the reciprocal in a calculator?
Okay, so there's two ways you can take reciprocal. And so take this over. So negative 0.375. Say you want to take the reciprocal of that. One way you can do it is now if you have the small calculator, see above the 7, there's an x minus 1. Right? So that'll do it for you. Okay. To do reciprocal. The other way you can do actually kind of like the main way to do reciprocal is one divided by. So you can do 1 divided by the answer, right? And see, this will just do reciprocal both ways over and over. Okay. You could do 1 divided by and type the number in.
All right, thank you.
Yeah.
Sorry, that was a bit of a stupid question.
No, it's okay. Yeah, because yeah, any question you have, there's probably a few guys who are wondering the same thing. Okay. All right, so you guys good on chapter 17?
Wait, what was question 66?
66, here, I'll, give you the notes on that. Okay. Yeah. All right, so let's go back to do refraction, right? Refraction. Right, number 7, index of refraction. A ray of light has an angle of incidence of 30 degrees on a block of unknown material and an angle of refraction of 20 degrees. What is the index of refraction of the material? Hey, that sounds exactly like the Snell's Law lab that we did last week. Guys, we're trying to figure out what's the index of refraction of this material. And you guys remember I was shining this laser light through. We broke out the protractor. We were measuring angles with respect to the normal line, that whole deal. Okay. So I just got the textbook version of that. We can use Snell's law. Snell's law. You guys remember Snell's law? Where is it's this first one right here. Here's Snell's law. Right? Index of refraction times sine of the angle is true on both sides of the material. Right? Okay. So this could be like the incident angle, this could be the refracted angle, for example. I do want to draw this out for you guys. Let's draw this out. So we got some barrier between some material. It's some kind of glass, for example, right? And maybe like air. Right? Okay. So you guys remember the angles that we're measuring with respect to are going to be with respect to this normal line. Right? That's the angles. Okay. Okay. And I've got I'm shining this laser like this direction. It's like here's my laser. Okay. We got a 30-degree angle here. So here's my laser pointer. Here's 30 degrees. I can call that the angle of incidence. Okay. Angle of incidence. Okay. And air, guys, what's the index of refraction of air? Yeah, like pretty much same as a vacuum, like 1. So we're just gonna call it. It's like 1.0003. I think it's not. We'll just call it 1. Pretty much it's right. And this material, now we'll call it like N2, and like we're solving for N2. What is N2? Okay, and this is going to refract. Now, anytime the index of refraction increases, it actually bends closer to that normal line, and which is exactly what goes on here. You got 20 degrees, something like that. Okay. All right, so N1, which could be just air, 1.0, okay, times sine of 30 degrees. Review. Guys, what is sine of 30 degrees? 1/2, right? 1/2 exactly. Right? You guys know that? Right? You guys see that like a bunch of times in here. Right? Use that over and over. N2 we're solving for. And sine of 20 degrees. Okay. So the answer is whatever sine of 30 degrees divided by sine of 20 degrees is. All right. 1.46. Boom. Okay. Actually, that is pretty close to this glass plot. I think we were getting numbers that were kind of in that ballpark. 1.5 something. Yeah, there you go. Okay. Okay, all right, number 67. This one looks nearly identical. Okay, we got air, we got some mystery liquid, we got the angles. Actually, this is almost identical to what we just did. It's just a 22-degree angle is the only difference, right? And then, so that's part A is just to do instead of. Then part B says, hey, what could that liquid possibly be? And they're going to refer us to the book. So let's take a shortcut for part A because we already have the setup. We already know that the index of refraction is going to be sine of 30 degrees divided by, in this case, sine of 22 degrees because we just did all the work for that, right? Navigate Snell's law. So sine of 30 degrees divided by sine of 22 degrees. Look at it, 1.335. Okay. Okay. What is this probably? What material is this?
Water.
Yeah, water. Right. So it's got to be water, right? Okay. But let's go ahead and so this is part A. That answers part A. Okay. Now part B. It's part A. Okay, so I mean, it's got to be water because that's one of the indices of refraction. I told you guys. It's a table 18. Where to go? 18.1. Table 18.1. Okay. So find the table in the book. Let's see what options they had. Actually, I'm glad they're saying that's on this list anyway. Because hey, look at that. We got different okay, got the straws in these different liquids, and it looks like they've been different. Right? Here we go. Here's table 18.1. Okay. Indices of refraction. Ooh, for yellow light. Hey, almost forgot that detail, but do you guys remember how different colors of light actually refract differently? I've been using a red laser. Okay, so I mean that is true. All right, and then 1.33 is water. Boom, there you go, it's water. Okay. But here it is for other materials. So like ethanol. Okay. Right. Here's remember I told you guys that different kinds of glass might have different indices of refraction. Okay, so there you go. There's different kinds of glass going on. Here's quartz. Right. Quartz, one thing helps make your watch keep track of time, right? Since we're breaking open textbooks, I want to bring up. Here it is. I got a forensic science book here. I'm just going to bring this up at some point today. Because one of the chapters in the forensic science textbook has to do with glass. And suppose you go out to a crime scene, right? You're trying to gather what little evidence there is. Maybe there was like shattered glass somewhere. And where did this shattered glass come from? Because I think if we could match the shattered glass to something, we could maybe it's like a hit and run, and we got to find the guy's car or something. What kind of car did this come from? Well, what glass was used? Okay? But you probably don't have a really nice like flat sheet of glass where you can like shine a laser through it and measure the angles. So how do you get the index of refraction of that glass? So therefore you can match the glass to some source, sample the source. Okay? And what they'll do is they'll use this method, and there's a little bit different variations on this method. Okay? Where if you put the little glass fragment that's all like jaggedy and it's really tiny, okay? In this textbook is showing different types of liquid. If the index of refraction of the liquid matches the index of refraction of the glass, like if one's exactly 1.53 and the other one's also exactly 1.53, okay, then what's it going to look like? Completely invisible. Like you wouldn't even know the glass was in there. It just totally disappears because there would be no refraction from the liquid to that little glass fragment at that point. Right, the light would just straight line through. Right, so it would look completely invisible. Okay? I've seen a version of this where there's some liquid they can use. I don't know the liquid where they can change the temperature, and by changing the temperature of the liquid, that actually changes the index of refraction of that liquid. Okay? And so then so they just adjust the temperature until that glass fragment disappears. And they say, right, at this temperature, we know the index of refraction of the liquid is like 1.53. Therefore, that's what the glass is. And then they can figure out which glass came from. Okay. There's a little bit of forensic science crossover right there. 75. The index of refraction for ground glass is 1.53 for violet light and 1.51 for red light. Remember, the red does not refract as much as the violet does. That. What is the speed of light in ground glass, right? And for each of those wavelengths? Violet on one end of the spectrum, red on the other.
Sorry, you might try 67 real quick.
Oh, yeah, there you go. Okay. So 67 has the exact same work behind it as 66 did. So, and it's cut straight to that point. So you start from Snell's law, you rearrange Snell's law. Okay. The only, even the numbers are almost exactly the same. Just instead of 20 degrees, it's 22 degrees. Okay. All right. So this goes back to sort of like, what was the definition of index of refraction? You guys remember it was like how much light slows down in that material. So index of refraction is the speed of light in a vacuum compared to the speed of light inside the material. Right? Which is always going to be something larger than 1 or equal to 1 for a perfect vacuum, right? This would be C over C for a vacuum. So they told you one of these things, you know one thing, and we're trying to solve for this V, basically, right? Okay. So part A for violet light. Okay. Well, here, Can you guys rearrange that and get V is equal to C divided by N? So that's really what we're gonna use, right? We're gonna just rearrange a little bit. You guys can do that, right? Do some algebra. So the speed of light for violet. Okay, so speed of light for a vacuum, inside a vacuum is 3 times 10 to the 8 meters per second. And the index of refraction for this crown glass for violet light is 1.53. Okay, now 1.53 that has no units attached to it because I mean meters per second compared to meters per second cancels out. It's just a number. What is 3 over 1.53? Okay. So 1.96, and then still times 10 to the 8 meters per second. Follow up for red light, right? So the long part of the spectrum, the longest wavelength your eyes can see. 3 times 10 to the 8 meters per second. Divide by 1.51. Right, and that is 1.99 times 10 to the 8 meters per second. Ooh. So a little bit faster, right? The fact that violet light slows down a bit more than red light does, right, is an indication that it's going to refract more, bend more, right? So we shine white light through a prism, it's going to refract out the different colors, right? Colors separate. Guys good? 76. The critical angle for a special glass in air, or so some kind of glass, is 41 degrees. What is the critical angle if the glass is immersed in water? Ooh, that's a good one, right? Straw this up. So, did I ask you guys the question about like a magnifying glass under the water? Right? Like how would this magnify compared to in air? Because let me just make up a number. Let's say the index of refraction of this glass is like 1.5. Right? For the air, it's 1.0. Okay. So the fact that there's a difference in index of refraction means that there's going to be some refraction and then we've got some magnification because it's a lens. Okay. But if I hold this underneath the water where the index of refraction is close to 1.3, 1.3 versus 1.5, that's not as much of a difference. So this isn't going to magnify as much underneath the water, right? So then even things like the critical angle is going to be a little bit different too. Okay. So let's go back to Snell's law, 76. Okay, Snell's law, where n1 sine theta 1 equals n2 sine theta 2. Okay. Now, if we're going from air to this glass, let's start with that. Let's start from air to glass, because that will allow us to solve for the end of the glass. Right. So it's going to be like a two-part problem. Right. Starting the air, and then later on we'll go to the water. Okay. So for air, index of refraction is 1. Okay. Now, what is the critical angle if we're talking about what angle should I put in right here? We did this with you guys' lab. Figure else out. So you got a glass. Okay. So we're doing like critical angle. Hemisphere glass. Pick out the pink ink. So 41 degrees, right? Let's say shine in a laser light at 41 degrees right here. Right? And it refracts just to the point where it's about to be total internal reflection. Like that. That would give away the critical angle, wouldn't it? If you didn't see it before, I bet you see it now. What angle is this right here? 90 degrees. Okay, isn't that? Maybe we should do it this way, in a little corner, like 90 degrees. Okay, that is going to, well, since that's on the side of the air, that would feed in right here. Okay. So sine of 90 degrees. Okay. A lot of you guys probably also know what is sine of 90 degrees? 1, right? So isn't this whole thing here just 1? Okay. Whenever we're talking about critical angle, then some part of Snell's law usually simplifies to that. Okay. Then in 2, okay, we're trying to figure out what kind of glass is this. So we're solving for that. And the angle that corresponds to is 41 degrees. So I see if you take sine of 41 degrees and just divide it over. So the end of this glass is 1 over sine of the critical angle, 41 degrees. As long as it's in air. Okay, and this is part 1 of this problem. Remember sine 41. I'm looking at 1.524. I'm saving a few extra digits. That's probably crazy precision, but that's part 1 of 2. So I'm gonna save some digits. Okay. Yeah, that's pretty consistent with like head-foot values for an extra refraction glass, and also what we found ourselves with Snell's law. I think we got numbers that were pretty close to that for this glass block. Okay, now we're going to take that and we're going to say, hey, how would this work underneath the water? Okay, so let's draw this thing underneath the water. Give myself some space here. So this could be like air and glass. This is going to be water and glass. Go back to this. Got a normal line. Okay. Now the fact that it's not going to refract as much, do you think that the critical angle for this glass underneath the water is going to be more than or less than 41 degrees? It's not going to refract as much, right? I'm thinking it's going to be more than 41 degrees. Moving on to that backwards, but we'll see. Okay. I think it's going to come in kind of like this would correspond to like almost total internal reflection. So we're trying to figure out what is theta C for the scenario where this is still 90 degrees. Right? There's that. Right. Now the index of refraction of the glass doesn't change, it's still the same glass. Okay. Change heat color here. Let's break out the green. How about that? We're going to start out over with Snell's law. N1 sine theta 1 equals N2 sine theta 2. Okay. Okay, let's do the water on this side. No. Yeah, okay, fine. Let's do water on this side. So for water, wouldn't the index of water be 1.333? So call it 1.33. Okay. Okay. And the angle, guys, what angle should I put in for the water here? How about this 90 degrees right here? Okay. 90 degrees, okay, is equal to, right? Oh, this N2. What feeds into this N2? This number right here. 1.5, because that's the glass. 1.524 index of refraction of glass. I'm not going to attach any units, unitless, times sine of the new critical angle that we're solving for. We're trying to figure out what is this theta C. Ooh. So we're a couple of steps away. Right? You guys see the 2 steps we have to do? Divide over 1.524 and then take the inverse sine. You guys see that? That's it. So sine of the critical angle is equal to 1.33 times sine of 90 degrees. Sine of 90 degrees, of course, it's just 1. All divided by 1.524. See what this crazy step is. 1.33 divided by 1.524. Okay. So all this stuff comes out to be 0.8727. That's sine of the critical angle. Okay. What's the very last step? How do you extract that angle? Take the inverse sine. Yeah, inverse sine to both sides. So inverse sine of that. So theta C equals inverse sine 0.877. Okay. 60.77. I'll call it 60.8 degrees. You could just say 61 degrees even. Okay, so about 61 degrees. Okay. Oh yeah, that is the way I drew it. Okay, so I did draw that right. So the critical angle is larger than it was before. Okay. It goes hand in hand with the magnifying glass. It's not going to work as well underwater because there's not as much refraction because the 2 indices of refraction are pretty close to each other. Right. Here's the right, now, since we're talking about index of refraction and water and stuff, there was something I said that I don't think is exactly accurate a few days back, so I want to go clear something up. It has to do with one of the posters hanging above my ceiling. Do you guys see the guy in the boat, like looking for fish? Right? So there's like a fish in the water over here. There's like a guy in the boat here. Okay, and I was making the claim that this guy would not be able to see this fish because like water refracts stuff. And I went back and think that okay, that's not exactly true. So draw some refraction lines. So like if the water was not there, suppose he was just like floating around in a blimp, and this fish was just like flying around. Clear shot. He said, "Okay, I clearly see the fish. Right, it's clear there. It'd be like a straight ray. Boom. Okay. But because there's refraction, whatever ray of light is headed towards them, I mean, at that point, it would just be total internal reflection. Okay. It's now only the critical angle. We try to get the critical angle sort of. It's probably right about something like that. I think it's like 40 something degrees for water. Okay. At this point, it'd be total internal reflection. Okay, so any light that did refract would just like barely go out. Okay. So a light ray that goes this way is going to refract out kind of like that. Okay. Goes up, it still goes straight up. Okay. There is actually a tiny sliver of light that would reach the sky. And same thing is true if you break out the glass block. I think it made a case like you shine a laser through, like with his, got a couple of ants crawling around and they'd be able to see each other. I said they wouldn't. I thought, wait, hang on, that's not exactly true. If you like move the laser a little bit, they'd be able to see a little sliver of each other. And maybe they look really skinny or something. Okay. And there is a tiny, tiny, tiny sliver of light. You go like this way, where it's just before the critical angle. It could just barely enter this guy's eyes. Now, what would it look like to this guy? Instead of looking like a big old fish, it would look like a little tiny skinny fish. And he wouldn't say like, oh, it's that direction. He would say, it looks like it's coming from this direction. So he sees like a tiny, tiny little sliver, and he thinks it's like just beneath the water, even though it isn't. Okay. All right, guys, sir. All right. Swimming pool lights. Ooh, all right. So light source located 2 meters below the surface of the swimming pool and 1.5 meters from the edge, right, just like in the figure. The pool is built to the top of water. At what angle does the light reaching the edge of the pool leave the water? Right. So how does it refract out? I think it's going to refract out more horizontally. Right? And that because the index of refraction of water is greater than for air. And follow-up question: does this cause the light viewed from this angle to appear to be deeper or shallower than it actually is? Oh, well, you can take my explanation for the fish and answer that question, right? Like this guy looking at the water says, "Ooh, looks like I see a little skinny fish just barely beneath the surface," whereas the fish is actually like really big and really deep, right? So you think it's like closer to the surface than it really is, right? Because that's what it appears to be. Same thing is going to be true here, right? There's like, okay, I'll draw this. I'll just one out on this paper. Go ahead and solve it. It's a 73. Okay. So, edge of a pool, 2 meters deep. Okay, and then 1.5 meters this way, there's like this light. Being, it's pool's full with water. Okay. And off the side, it was like someone standing over here. Okay, so this is all like water, right? So hatch in the water a little bit. Okay. Okay, now this light is sending out light rays in all directions, right? Up to the side. Okay. We're going to follow one particular light ray. We're looking at a single light ray that's headed right to the edge of the pool. Okay. I'll draw a normal line right at that point. Okay. And then that should refract out kind of like this. Okay? You can think of it both ways. Right? The fact that index of refraction of air is 1.0, and for water, it's 1.33. Right? Whichever has the greater index of refraction is going to refract closer to the normal line, right? Like this does. Or the other way, refract like further from the normal line, like more horizontally. Okay? So this angle is less than this angle. Right? So the question for A is like, what is this angle right here? Okay. What is that angle? Is question A. Okay. Well, first thing we have to do is figure out what is this angle in the water. Okay, and that we can get with geometry. Because they told you this distance right here is 1.5 meters. And this distance right here is 2.0 meters. Okay, so I'll call it theta sub W, like the angle on the side of the water. Okay, makes sense? How can you guys solve for what is that angle? Who can think of a way to set that up and solve that? This goes back to last semester stuff we did, geometry. Ooh, do you guys see a nice right triangle here? You guys see two legs of a right triangle that are given? Oh, two legs of a right triangle have a what relationship with each other? Sine, cosine, or tangent? Tangent. Ah, can I say that tangent of theta water is equal to opposite divided by adjacent? That's what tangent is, right? Opposite over adjacent. 1.5 meters over 2.0 meters. That's how we're going to get that angle. Okay. As long as you take a what of both sides? How do you undo a trig function? Take the inverse trig, like inverse tan. Okay, we just did that a couple minutes ago anyway, right? Can you guys say theta W equals inverse tan 1.5 over 2.0? Make the meters cancel, right? Just like that. Okay. It's also called arctan. I know it's the notation Microsoft Excel also uses. If you do a tan, if you say equals a tan, ATAN, then it'll go into those. And it'll spell out a number of radians, but that's how it does it. So inverse tan 1.5 over 2.0. Of course, we're using degrees. Okay, so in case you missed that, if you ever plug this into Excel, you have to do equals ATAN and then type in your ratio, something over something. Okay. And it will give you some number of radians. Okay, so that's the way it does it on a computer. Okay. We're doing degrees, and I'm getting 36.9 degrees. Oh, 36.9 degrees. Oh, I can't believe I didn't notice this before. That is a super recognizable angle. Guys, this is a what triangle? That is a 3, 4, 5 triangle. Yeah, I would slowly pick that up. That is a 3, 4, 5 right triangle right there. Okay. Okay. Now, how are we going to figure out this angle? We have to apply what starts with an S. Snell's law, right? So let's flip over to Snell's law. N1 sine theta 1 equals N2 sine theta 2. Solve for the angle. We should have these other three things. Okay? N of water is 1.33. The angle is 36.9 degrees. Or if you like, you could let's just a little backward way, a little bit more accurate way, actually. Guys, if this is a 3, 4, 5 proportional triangle, and sine is opposite over hypotenuse, wouldn't sine of this just be 3 this, right? 3 over 5? Let's try that. What is sine of the answer? 0.6. Yeah, that's 3 over 5. Because it's a 3, 4, 5 right triangle. That's what that is. A little bit different way to think about it. More accurate though. And then error index of refraction is like 1.0. Sine of theta on the side of error, theta 2. Okay. So divide over 1, that doesn't change the numbers. Inverse sine of all this stuff. So theta is equal to inverse sine of 1.33 times 3 this. Like that. Inverse sine 1.33 this. 52.9 degrees. About 53 degrees. 53 degrees. Okay. Oh yeah, that's that matches my picture. Okay, see how made this angle smaller than this angle? Right? There you go. Okay. Consistent with that. Ooh. All right, you guys good so far? All right, so that's gonna have to be a pause point because Belle's about to ring here in a minute. Yeah, but I got some other puzzles and demos lined up for you guys tomorrow.